Good evening, everyone. Welcome to our live chat for week two. Tonight, we're going to talk about database design and modeling. For our IP2, you have to create a ER diagram for the database that you're going to build in IP3. So whatever design you come up with for your database with the tables and fields, you'll use that design to actually write the SQL code that will actually build that database and populate those tables with some data. And we'll do some other fun things with that data once you get it in there. So we'll go ahead and get started. First, we're going to talk about the relational model. So the relational model, some terminology for you to know. A relation is a table with columns and rows. So another word for a relation is a table. And I provide some alternative terms because in my everyday workings with databases and stuff, I very rarely use the formal terms when referring to databases. We use some of the accepted terms like table, rows, columns, instead of relations, attributes, and all that other fun stuff. But it's good for you to know what those formal terms are. So the relation is the table with columns and rows. It only applies to the logical structure of the database, not the physical structure. An attribute is what a named column of the relation is. And the domain is a set of allowable values for one or more of those attributes. This little diagram shows what two different relations look like. There's one customer relation and there's a billing relation. So there's two new tables. They have attributes. In our customer table, we have the attributes of customer ID, customer name, and status. And in our billing table, we have invoice number, customer ID, and amount. This one shows you how those two tables are related by using the customer ID in one table as a foreign key in another, so that you can establish that relationship between those two tables and use that relationship to query data from both of those tables using some SQL statements. These are the formal ones that are underlined. A tuple is a row of a relation or table. I put the more common names in parentheses to try to make it a little bit easier for you to understand what those are. Degree is the number of attributes in a relation or a table. The cardinality is the number of tuples or rows in a specific relation or table. And a relational database is simply a collection of normalized relations with distinct relation table names. This diagram from our text shows all of those things in it's a very good diagram to refer back to. It shows relations, the branch and staff relations with attributes and what their relations, what those attributes, what the data is and the relations, and it explains the cardinality. It shows primary keys and foreign keys, how those two tables are related. So it's a good reference to look back at if you're trying to understand the different components of your table. This just gives you some attribute names and domain names, and then the meaning of what those might be, and then some possible domain definitions or ranges for some of these fields. You can use that as a reference. And again, you can download all of the PowerPoint slides from my website. I just uploaded updated version, copy one for unit one, and an updated version, which is this one for unit two. So they're both out there in a PDF form for you to use. Alternative terminology, with formal terms, we mentioned relation, tuple, and attribute. Alternative terms, one is more likely how people refer to database stuff, tables, rows, and columns. And you could also refer to those as file records and fields if you wanted to. A relation schema is the named relation or table, which is defined by a set of attributes or columns and domain name pairs. Relational database schema is a set of relation schemas, each with a distinct name. So every table, normalized tables with a distinct name. You can't have more than one table with the same name within the database because it won't let you do that, first of all, because the name has to be distinct. Properties of these relations or tables. A relation or table name is distinct from all the other relation names in that schema. Each cell of a relation or table contains exactly one atomic single value. So in one column, you wouldn't put customer IDs and order IDs all in one column because those are two different values. So it should have one distinct value in there. Every attribute or column has a very distinct name. You can't have two columns that are called order ID or customer ID or first name, last name. And then the values of those attributes or columns are all from the same domain, meaning you wouldn't have customer information in a table about products, right? You wouldn't put those all into one table. You would separate them into separate tables. And the same thing with customers and orders. You wouldn't put all of the customer information and order information in one table. First, in a relational schema, that wouldn't work very well. You would only ever have then one order for every customer because of the way those database tables are created with the primary key fields. You cannot be duplicated, so you couldn't add multiple orders. So that's why we separate it all into different tables, and we use different key fields to link those tables together in our SQL statements so that we can pull data from two. And we will show you more of that on week 3 when we get into the querying and building your database. Every row is distinct. There are no duplicate rows, or the order of the attributes or columns really has no significance. And then the order of rows has no significance theoretically. Every row is distinct. So you can't have 2 rows or 3 rows with the same information about your customer or orders in that database table, because then it wouldn't be normalized, right? We normalize the database by ensuring that there's the row is distinct by including a primary key field, which makes that row distinct because that key field can never be duplicated in the database. Relational keys, we have what's called a super key, which is an attribute or set of attributes that uniquely identify a row within a relation or table. Candidate keys is the minimal set of attributes that help uniquely identify each occurrence of an entity. And we can identify more than one candidate key, in which case we must select one to be the primary key, and then the remaining are called alternate keys. We're just going to focus on primary keys and foreign keys to make it easier for us for this class. A primary key is a candidate key, which is select to identify tuples or rows uniquely within that relation or table. A foreign key is an attribute or set of attributes. In our instance, it's always going to be one attribute. We're not going to use combination of values within one relation or table that matches the candidate key of some possibly the same relation. So in other words, your customer table has a customer ID. You want to use that customer ID maybe to join to your order table, right? So your order table would also have customer ID, and the customer ID in the order table acts as a foreign key. So the data that you enter into that foreign key field, the data, the actual value for the customer ID must be present in the database first, as in the table where it acts as the primary key. So customer IDs 1 through 10, your orders. So you would have to populate your customer table first, and then you could populate your order table with customer IDs, the foreign key values ranging from 1 to 10, because that's all you entered in your customer table as the primary key field. And we'll show you more of that and the kind of errors you get when you don't do that when we get to week 3 and we actually run some SQL code. Integrity constraints, null, which represents values of an attribute or column that is currently unknown or it's not applicable for now. It deals with actually incomplete or exceptional data. It represents the actual absence of a value and is not the same as 0 or spaces, which are actually values. Entity integrity, meaning in a base relation or table, there's no attribute of a primary key can be null. So you can't have a primary key failure value that's null. If the database won't allow you to do that, once you designate that field as a primary key field, it's going to require you to either enter the data into that column or set it so that it automatically increments a counter and adds a value to that table or that column every time you add data. We're going to just add data to that column every time when we insert our data. We're going to insert a value for our primary key fields. Referential integrity. So if the foreign key exists in a relation or table, either that foreign key value must match the candidate key value of some row in its home relation or table, or the foreign key value must be wholly null. We need to make sure that it has a value in our base relation table where it acts as the primary key, which I talked about a little bit earlier. Some general constraints, additional rules are specified by the users or your database administrator that help define or constrain some aspect of your enterprise, so they can put certain other constraints in place based on your business process and business rules for your organization. A view is a base relation or table. Named relation table corresponds to an entity in your conceptual schema, right, where the tuples or rows are physically stored in a database. A view, on the other hand, can be defined in terms of one of those base relations or tables. It is a virtual relation table, doesn't necessarily actually exist in your database, but is produced upon request at the time of the request. The contents of a view are defined in a query as a query on one or more of your base relations. So if you have a really complex database and there's a lot of complex joins between all these different tables, your DBA can create a query which will create the view for you, right? And then the view could be very simply have all the columns in it that you would need to query against. So when you write your query, you're writing it to view. So when you run your query, the view, the code that generates the view will run first. It'll populate dynamically all the data that the view is going to return, and then it will return the rows and columns that you actually requested from that view. They are dynamic. Changes made to the base relation or table that affect the view attributes are immediately reflected in that view because it's not stored in the database as a physical table. Purpose of views, they provide very powerful and flexible security mechanism by hiding parts of the database from certain users. Permits users to access data in customized ways. So the same data can be seen by different users in different ways at the same time. And you can simplify complex operations on base relations as I discussed. So if you have some sensitive data, let's say financial data within a database, but you need some information from that table that you have access to view, but not necessarily all of it. When the DBA creates a view, he can include only the columns that you are authorized to see, and omit the other data that may be more sensitive or that you don't have access to. So they're very customizable and they work very well as a security mechanism because you'd never be able to see the data that you're not allowed to see. So now we'll touch on entity relationship modeling. Concepts of the ER model, entity types, relationship types, and attributes, and we'll touch on each of those. An entity type is a group of objects with the same properties identified by your enterprise as having an independent existence. Entity occurrences are uniquely identifiable objects of an entity type. These are some examples of entity types, right? We have physical existence, a staff person, a property you own, customers, parts, suppliers, products. Those are all tangible, physical existent objects. Conceptual existence, viewing of homes, inspections of your site, sales that you make, or work experience that you might have. Those are all conceptual existence. They don't physically exist. Different relationship types, set of meaningful associations among your entity types. An occurrence, relationship occurrence is uniquely identifiable association, which includes one occurrence from each participating entity type. We have different degrees of a relationship, which is the number of participating entities in that relationship. There are 3 different types of relationships of a degree. 2 is binary, 3 is ternary, and 4 is quaternary. We can have what's called a recursive relationship, which the relationship type where the same entity type participates more than once in different roles. Relationships may be given role names to indicate the purpose that each participating entity type plays, and we have an example for you. So we have a table called staff table. So every member of staff is in this table, but there's also people that act as supervisors in this table. So they can have a supervisor role. So you would then have a recursive relationship back to this table to get the staff people and the supervisors. And this is how you could indicate that on a diagram. We're not going to worry about doing it that way. We don't need to identify role names or what our relationships look like. So it's just for your information to show how that would work. We have attributes. An attribute is simply a property of an entity or a relationship. The domain is a set of allowable values for one or more attributes. A simple attribute is an attribute that is composed of a single component with an independent existence, like customer ID or first name or last name. Composite attributes are composed of multiple components, each with an independent existence, like addresses or phone numbers, I believe. You have single valued attributes, holds a single value for each occurrence of that entity type. Multi-valued attributes that hold multiple values for each occurrence, and then a derived attribute, which represents some sort of value, which is derivable from values of other attributes in your database table. We talked about the keys before a little bit. Candidate keys, primary keys, which is I have with the red background. That's the important one we need to focus on in our class. The candidate key, which is been selected to uniquely identify each occurrence of an entity type. This diagram shows all of that stuff all in one little nice image. So we have our relations, staff and branch, right? We have our attributes for the staff table. We have primary key fields identified. We see a derived attribute in the staff table where they're calculating total staff. We have a multi-valued attribute in our branch table, which is the telephone number, and a composite attribute because it has separate meanings, separate parts for it. The address field, which has its street, city, and postcode. A strong entity type is an entity type that is not existent dependent on some other entity type. A weak entity type is existent dependent on some other. This shows an example of what a strong entity type might look like and what a weak entity would be. So client is a strong entity type, and preference is a weak entity type because it is existent dependent on the client entity itself. Some structural constraints. So the main type of constraint on any relationship is called multiplicity. Multiplicity is the number or range of possible occurrences of an entity type that can relate to a single occurrence of an associated entity type through any particular relationship. It represents the policies, which are business rules that are established by your users or your company. The most common degree of relationships is binary. Binary relationships are generally referred to as being either one-to-one, one-to-many, or many-to-many, if you've heard those terms before. This shows you what multiplicity looks like on an ER diagram. I know our in IP2 says something about including the cardinality, a multiplicity on your diagram. You don't need to do that. We'll make our diagram fairly simple with just having the tables and fields in the tables, and then the crow's foot notation on how those tables will be joined together. But this shows that this is a one-to-one relationship because every branch is managed by one staff member, and a member of staff can manage 0 or 1 branch, and that's how you would indicate those. So that's the multiplicity, those little numbers on the ER diagram. And those numbers represent different parts of this relationship. This is a one-to-many, what a one-to-many would look like. And then this multiplicity is made up of 2 types of restrictions, right? Cardinality and participation. We have to identify the cardinality in our IP2 in the word table. If you've downloaded the sample paper, look in IP2 in that paper, you'll see a very nice word table that has our entities, attributes with data types, relationships, and cardinality. I'm not going to grade heavy on getting the cardinality right. Just take a shot at it and see if you can get the cardinality correct for your specific relationships. But make sure you include that table because the missing that table, I need that table in there. There's only a few parts to IP2, that table, your ER diagram, and I think the analysis section, and some listings of some business rules and subjects of interest, which are the tables in your database. But the cardinality, that multiplicity is made up of both cardinality and participation. Participation determines whether all or any of some entity occurrences participate in a particular relationship. This shows there's the multiplicity, and it shows you which ones are cardinality, which is always the number on the right, and the participation is always the number on the left. And it gives you an example of what that looks like and how you would indicate. We're going to talk about normalization, which is what we need to do to our database table. We need to normalize it because it's a relational database table, a relational database, and those are normalized. So how do we do that? And what is normalization? It's a process or a technique which is used for producing a set of suitable relations or tables that support the data requirements of your enterprise. Characteristics of a suitable set of relations or tables include minimum number of attributes or columns necessary to support the data requirements of your enterprise. You wouldn't necessarily want to have a table with, let's say, 100 columns in it because that doesn't make sense. It's too big, first of all, for the database to handle. And if you start loading it with a lot of data, it's going to really impact your performance. The attributes or columns with a close logical relationship are found in the same relation, like we talked about earlier. You wouldn't have customer data and order data in the same table, right? And then there's minimal redundancy with each attribute or column represented only once, with the important exception of attributes that form all or part of your foreign key. So you wouldn't duplicate columns because you can't duplicate column names anyway, because the system won't allow you to do that. The benefits of using a database that has a suitable set of relations is that the database will simply be easier for your users to access and maintain that data, and it takes up minimal storage space on the computer. Because if you normalize it, right now you have unique rows in every table, so you're removing the duplicated data that you may have in some other systems or some flat file systems, and it does shrink the size considerably. The major aim of a relational database design is to group attributes or columns into those relations or tables to help minimize that data redundancy. We talked heavy about that. Potential benefits for implementing databases include updates to the data stored in the database are achieved with minimal number of operations, thus reducing the opportunities for data inconsistencies. Reduction in the file storage space required by your base relation or tables, thus minimizing costs. There are some problems associated with data redundancy are illustrated by comparing the staff and branch relation with the staff branch relation table on the next slide. So here we have in our table, our database table, they have a table named staff and one called branch. And then they created this table called staff branch. Notice the staff branch table is just a combination of both of those tables together with repeating data for the branch address, which causes issues with updates and update anomalies not being, if you don't update all of the correct data rows, your data is now out of sync. So that staff branch relation table has redundant data. Data details of the branch are repeated for every member of staff. So in contrast, the branch number appears only once for each branch in the branch table, and only the branch number is repeated in the staff relation table. So you see we had the branch number and the branch. So here we have branch number in this table, and it joins back to this. So in this table, branch number is the primary key field, and in this table, branch number would act as the foreign key. So this way, if you ever have to update the address for a branch, you only have to update it once in this table. In this setup down here, if this address ever changed for 163 Main Street, if they ever moved that office, you'd have to update in this table 3 rows, 1, 2, 3, as opposed to 1 row in this table. The relations that contain redundant information may be potentially suffer from update anomalies, as I just talked about, right? If you have it in multiple, if you don't update all the correct rows in that table, and now you have that branch with 2 different addresses in your system, right, which is not good. The process of normalization is a formal technique used for analyzing a relation or table based on its primary key and any functional dependencies between those attributes. It's often executed as a series of steps, right? Each step corresponds to a specific normal form, and we'll talk about at least 3 normal forms that we'll go through. And they all have very known specific properties of each of those. As normalization proceeds, the relation or tables become progressively more restricted or stronger in format, and also then less vulnerable to update anomalies. So the process of normalization, you'll see this little image here has the first normal form of 1NF all the way up to 5th normal form, and then there's some maybe even higher than that. There are 3 normal forms were originally presented: first normal form, second, and third. R. Boyce and EF-Codd introduced a stronger definition of third normal form called BCNF, or Boyce-Codd normal form. Higher normal forms, higher ones were then later introduced that go beyond that, and those are out of the scope for this class. We're going to talk about first, second, and third normal form, and that's about as far as we'll go with our database table. You start with an unnormalized form, or UNF, right, which is the table which contains one or more repeating groups, simply creating a table by taking data from some information source like a form you may have, right, into a table format with columns and rows. First normal form is that relation or table in which the intersection of each row and column contains one and only one value. So we need to go from UNF to 1NF. We have to first nominate an attribute or a column or a group of attributes or columns to act as a key for the unnormalized data table. In our instance, we're going to use 1 column. We have to identify the repeating groups in the unnormalized table, which repeats for that key attribute. And then we either remove the repeating group by entering appropriate data into an empty column of rows containing the repeating data, which simply is flattening the table, or by placing the repeating data along with a copy of the original key attribute into a separate relation, which we did in this diagram here. So this student table is our UNF, right? It has repeating groups, which is a violation of first normal form. We broke it into two separate tables, a student table and then a student course table. Notice we took the information at the top from this table and put it into our student table with the student number as the primary key field to make every row unique. And then we took this course ID information, we put it into a student course table where we have our student number as a foreign key, and then the course ID is the primary key field for that table. And then we just list that. So then by joining on student number, we can display different courses that student may have taken. So this is a one-to-many crow's foot notation, right? One student can take many courses. There's no repeating groups, so that's our solution for first normal form. Second normal form is based on this concept of a fully functional dependency. This indicates that if A and B are attributes of a relation or table, then B is fully dependent on A if B is functionally dependent on A, but not on any proper subset. And we'll show that the same example as I did there. A relation that's in first normal form, right? It has to be in first normal form first. And every non-primary key attribute is fully functional dependent on the primary key. We go from first to second by identifying the primary key for that first normal form relation. We identify the functional dependencies, and then if partial dependencies exist in the primary key, remove them by placing them in a new relation along with a copy of their determinant. So we have a table called students, which has information about students and professor IDs and professor names and grades. So we're going to break that into its three separate different components, right? After normalization, we put students in one table, we put professors in another table, and then we create another table with grades that can link to two of those two tables and provide the grades. The headings on this grid, where I got the screenshot, this heading is wrong. So this is ID student, ID professor is actually this column here, and the grade is actually this column that's off by 1. So we only have the IDs and the grades in this table, and we can join back if we want to know who is student 1 that got a 5 in this class. We just link back to this table on the student ID in this table and the ID student in this table, and we can find it. Oh, that's Mueller. Okay. And then we have third normal form, which is based on a concept called transitive dependency. Transitive dependency is a condition where A and B and C are attributes of a relation such that if A is dependent on B and B is dependent on C, then C is transitively dependent on A through B, provided A is not functionally dependent on B or C. A relation that's in first normal and second normal form. So we have to go, remember, from first to second before we can get to third. Which no non-primary key attribute is transitively dependent on primary key. I included a little definition down here of what transitive dependency is with a link in the PowerPoint slide. If you want to learn more about that, you can click on the link. There's some more information on that website for you. This might be, I don't know if this might be hard to see. I try to make it as big as possible for you, but to go from second to third, we identify the primary key in the second normal form relation. We identify the functional dependencies in the relation or table. And then if transitive dependencies exist on the primary key, we remove them by placing them in a new relation or table along with a copy of their dominant. So this we had on the left here is our second normal form, where we have this one in the middle here, which has a table called employee. Notice in this one down here, we break out some information from that employee table to a table now called job. So we have a job and it has the job class and the charge hour. And that job class would link back to our employee table where the job class exists as a foreign key, because it must be transitively dependent on that data. So that's third normal form, and that's as far as we go for our data in our database table. This is just some general definitions of second normal form and third normal form, which we already talked about. The purpose of normalization data, it's to identify a suitable set of relations that support your data requirements of your organization. A suitable set of relations includes minimal number of attributes necessary to support your data requirements, attributes that have a close logical relationship, which we talked about, and then minimal redundancy with each attribute represented only once. So that's the live chat portion. We'll talk about our Unit 2 individual project. And I stress, if you haven't downloaded the template for the IP document from my website yet, you need to do so before you submit IP2 and put your information from IP1 into that template. That template already has an automated table of contents with all of the headings in it. So that way it makes it easier for you to do that. So this project deliverables are as follows. We have to list a subjects of interest or your proposed entities or tables. It's just simply a bulleted list of the tables you're going to include in your database. They give you 3 of them to begin with: customers, orders, and products, and you have to add a minimum of 3 of your own subjects of interest based on your retail store. So with this layout, the way that this is with customers, orders, and products, with the order table being the only table you store orders in, one customer can only can't have multiple products on an order with this structure, right? Because of the way the order table works. Orders has that order ID. It can't be duplicated multiple times in that table because it's the primary key field. So I'll show you on week 3, but you can add another table to help overcome that limitation by adding a table called order line table. So if you want to add a table called order line to your database, you can use that one. And I'll show you how that works when we do IP3, when I go through that live chat. And then the second live chat for that week, where I actually show you how to make changes to the SQL files. But you would simply do order line table. So you have an order line ID. You could have order ID as a foreign key and product ID as a foreign key. So now a customer can order 6 different products on the same order, because the order ID can be duplicated because it's a foreign key field, not a primary key field. So you can duplicate the order ID number multiple times with different product IDs, and you would have different order line ID numbers for every single row. So that gets you past that limitation of only having one product on an order. They give you 3 business rules that you must adhere to. Each product is assigned to a maximum of 1 category. A person placed at least 1 order as a customer, and then all the products have a minimum reorder level. And then just make up 3 of your own business rules, and let's list those in a bulleted set like we have here, if you like. Then you have to include the list of business rules, right? Your tables, include a list or a table, and I want a word table for your entities, attributes, including data types, relationships, and cardinality constraints. So again, see the sample paper provided for the format and the contents. There's a really good Word document table in there that you can use as your guide. And then you have to include an entity relationship or ER diagram. It's including data types. Don't worry about adding the relationships with the degree and cardinality constraints. Or you don't even need to worry about adding the data types to the ER diagram. If you just add the entity, the table itself with the attributes, the names, that's fine. Okay, what happened to my screen went crazy on me. And then verify the data is depicted in the ER diagram. Here's to a minimum of 3rd normal form. If it doesn't, then just give some justification why. Okay, so now my slides are frozen for some reason. Let me stop the share. Let me try sharing it again. Okay, 1 second. We were just about at the end anyway. Slideshow. It's acting strange. It won't let me. Okay, let's see if we can go. There you go. And then remember to provide your analysis of how this project fulfills the mission and one or more goals of your case study organization using Microsoft Visio. And I did post a video, I believe, that shows you how to create an ER diagram in Visio if you have Visio. I don't think the version of Visio that they give you at the university has the database component or the ER or the crow's foot notation. So I provide a list of online resources that are free that you can use if you like to create your diagrams. And then of course, make sure you cite everything in text and references using APA. Name your document exactly the way it shows it here, please, and then submit your assignment. And then again, my email address is here. You have it in the classroom as well. I have office hours on Thursdays and Saturdays, and any other time that you really need to meet, just go to my website and set up some time if you need a one-on-one. Our live chats are every Wednesdays at 6 o'clock, not 7. Any comments, questions, concerns, or questions on anything that we've covered, or anything from week 1 that you might have questions on? Feel free to unmute yourself and ask anything you'd like. Okay, good. Thank you, Zachary.
Sir, I did have a question on the tables that we'll be using for this IP. How deep do they need to be? Is there a minimum, maximum?
No, you make it as big as you need to make it to meet your business needs for your organization. I mean,
Okay, sir.
right, logically, a customer table might have, right, the customer, have your customer ID as your primary key field, right? Then you have their first name, last name, then their address. And I would break I think the textbooks shows the address as one field, and then it has the address, because it's like European, they have the whole address in one field called address. I would break the address into its component parts. So address 1, address 2, city, state, zip, and then you might get their phone number and email address, right? If you need something like if they have a membership in some program you're doing or something, you could capture that in there as well. So you only really need a handful of fields in that table. And the order table, a good way to figure out what you need to look at. I don't know if you can't see week 3 yet, can you? No, you can't see the week 3 project in the classroom, can you?
No.
Because that, I don't know why they do that. Maybe I'll send something to the class, because if you look at the reporting requirements for the IP3, it tells you what you need to report on, right? So if you don't have those elements in your database table, you can't very well report on them. Then I think one of them is called category. So you need a product category. So either in your product table, put a column called category, or create a category table if you want, and add some categories to it and link it to your products table, right? So you can report on, because they want to know a number of orders by category, I think is one of the queries they ask you to do. But keep in mind, this is an evolving process, right? You're going to do your IP2. By the time you get to IP3, you may realize, oh, I need to make changes to my database structure. And that's fine. You can do that. But you can change the table structures. You can add columns. You can take columns away from tables. You can change data types from what you put in your IP2, right? Because that's a living, breathing document. You can update it with whatever changes you make in IP3. If you realize you need another table, or you need additional fields in this table, or you have too many fields in this table, you can change it, right? You're not stuck to whatever you're going to put in IP2, right? So just try to think of it logically. What kind of, if you were really running this store, what sort of information would you really need to capture for your database so that you can do some accurate reporting?
Thank you, sir.
All right, you're welcome. Well, I appreciate you guys coming and sitting with me tonight. Have a good evening with the rest of it, and I'm here if you have any questions or need anything.
You too. Thank you.
Thank you. Good night.